Hello everyone, I am Professor Jagadeesh Hugar. So in this video, I am going to explain you the introduction to the cylinder and what is the meaning of a cylinder, what are the classifications of cylinders and theory related to the thin cylinder and problems related to the thin cylinder. So first of all, what is meaning of cylinder? So we know it is a tubular object where it is having tubular circular object where it is having some thickness and having the inside diameter. So here you can see, so this is di means it is inside diameter and T means it is thickness of the cylinder, and Pi represents the inside pressure due to the whatever the fluid present in the cylinder. So cylinders are classified into two types. So cylinders are classified into thin cylinder or spherical vessels and thick cylinder. So cylinders are mainly classified into thin cylinder and thick cylinder, and spherical vessels and thin cylinders are based on the same concepts, means same thickness formula is used. So basically cylinders are classified into thin cylinders and thick cylinders. Thin cylinders, when we can say cylinder is thin cylinder, if di by T is greater than 20. So if this ratio means inside diameter to thickness ratio is greater than 20, then we can say cylinder is thin cylinder. Otherwise, if the thickness is less than di by 20, then we can say cylinder is thin cylinder. So these thin cylinders are used in low pressure boilers and used as a storage tanks. So means wherever the pressure is less, so in that cases, so thin cylinders are used. And what is the meaning of thick cylinder? Thick cylinder means if the ratio of di by T is less than or equal to 20, so then we are going to say cylinder is thick cylinder. Otherwise we can say T is greater than or equal to di by 20, then we can say cylinder is thick cylinder. So these thick cylinders are used in the high pressure boilers, hydraulic cylinders, gun barrels and reactors. It is like nuclear reactors, thermal reactors. So means basically thick cylinders are used where the pressure is high. So as the thickness increases, its pressure capacity is also increases. So that's why thick cylinders are used in the high pressure applications. So let us see about the thin cylinder and whatever the theory related to the thin cylinder and problems on the thin cylinder. Okay, so here you can see thin cylinder in stresses in thin cylinder. So basically in cylinders, so there are three types of stresses will be induced because of the whatever the fluid inside the cylinder. So here you can see, so this is a Pi, that is inside pressure. So because of this, so there is a stress is going to induce in the cylinder. First one is longitudinal stress. So longitudinal stress means, so this stress acts parallel to the axis of the shaft. And next is circumferential or tangential or hoop stress. So this stress acts along the circumference of the cylinder. So in this direction, along the circumference. So you can see along the circumference of the cylinder. So next is radial stress. So radial stress acts in the radial direction, means, so suppose you can see it is exact, radial stress is exactly opposite to the pressure applied, means, so let us say here there is a fluid which, because of which there is some pressure, so pressure acts in this direction, okay, and radial stress will act in the exactly opposite to this pressure. So radial stress at the inner surface is equal to internal pressure, but it is in opposite sign. Suppose if I say pressure is 10 kilopascal at the inner radius, then radial stress at the same point it is minus 10 kilopascal, means it is same, equal in magnitude but opposite in direction. So let us see one by one different type of stresses. First one is circumferential or hoop stress or tangential stress. This stress exerted circumferentially on every particle in the cylinder wall. So you can say this can be imagined as band surrounding the barrel, means there is some surrounding around the barrel. So in that way this stress is going to act. When barrel expands, the band stretches and undergoes stress. So suppose when you place something here, so because of that, so cylinder will try to expand. So at that time, so this stress will act along the circumference of the cylinder. So this basically will stretching the shell circumferentially. Okay, means it will try to increase the radius of the cylinder. Next is longitudinal stress. Longitudinal stress acts in the longitudinal direction. Longitudinal direction means parallel to the axis of the cylinder. So here we can say, so this is the longitudinal stress. So at any point it is acts in the direction parallel to the axis of the cylinder. And next is radial stress. So radial stress, it is mainly due to the design pressure, means whatever the pressure due to the fluid inside the cylinder, so because of that, so this radial stress is going to act. So as I said, so thin cylinders are used for low pressure applications. As the pressure is low, then radial stress will be very low, means very less, as compared to the sigma T and sigma L. Because radial stress sigma R is totally depends on the inside pressure. So as the pressure decreases, so its value also decreases. So because of low pressure, so its value is very small as compared to sigma T and sigma L. So that's why, so radial stress is neglected in the analysis of thin cylinders. Means in thin cylinder calculations, radial stress is not considered. Okay, that means we are going to consider only circumferential and longitudinal stress in case of the thin cylinders. Next is to find the equations of sigma T and sigma L. So first one is, let us find the equation of sigma T, that is tangential or circumferential or hoop stress in thin cylinder. So here you can see, so this is the cylinder, so this is cut in the longitudinal direction. So this is inside, Pi means it is inside pressure due to cylinder, inside pressure due to fluid present in the cylinder. Di means it is inside diameter of cylinder, L means it is length of the cylinder, T means it is thickness of the cylinder. So here only 50% of cylinder is considered. So this 50% is considered here, you can see. So this is Pi, inside pressure, this is thickness. So sigma T means it is stress which is acts in the circumferential direction. So this is sigma L and this is sigma T. So the same sigma T that is in the circumferential direction, and L means it is length of the cylinder. So here, whatever the pressure it is acting, force due to this pressure should be equal to the resistance force offered by the cylinder for equilibrium. So that concept we are going to use here. Pi means it is inside pressure into projected area, means force acts in this direction on the cylinder is given by pressure and projected area of this projected area. Projected area means it is this diameter into length. So suppose if you project this on this some plane, so it is rectangle. So it is rectangle means it is di into L. So that is Pi into projected area means Pi into di into L is equal to, this is applied force due to pressure, and resistance force is given by, so whatever the stress induced in the circumferential direction sigma T, and its resisting area means you can see here, so this thickness into L plus this thickness into L, that means it is 2 times thickness into L. Suppose if you project this area on the plane, means this is T and this is L, and this is T and this is L, means T into L into T into L, that is so 2T into L, that means 2 times thickness into L. So that's why it is 2T into L. So afterwards sigma T will be given by Pi into di by 2T. So if you simplify this, so L will get cancels. So sigma T will be given by Pi into di by 2T. So here you can say, so Pi into di by 2T into eta L. So eta L means it is longitudinal joint efficiency. Means cylinders are manufactured by using the joints. So whatever the efficiency of joints in the longitudinal direction, so that efficiency will be considered. So if nothing is given in the problem, so you can just take it as a eta L is equal to 1. That means it is 100% efficiency. So here you can see hoop stress assumption. Hoop stress is uniformly distributed throughout the T, means throughout the thickness. So it is only applicable for thin cylinders. In actual, hoop stress is not uniformly distributed, means it is maximum at the inner surface and minimum go out, decreases and becomes minimum at the outer surface. But in case of the thin cylinder, we assume it is uniformly distributed throughout the cylinder, throughout the thickness. Next is longitudinal or axial stress. Again, if you consider the cylinder, so 50% of cylinder, so you can see pressure, force due to pressure acts in this direction, and that is resistance that is resisted by longitudinal stress, which acts in the opposite direction. So for equilibrium, so force due to this longitudinal stress should be equal to the force due to inside pressure. So force due to inside pressure is given by, so this is a circular cross section, that is pi by 4 into di square. That means force due to pressure is given by Pi into projected area. So if you project this area, so that will be pi by 4 into di square. Pi into pi by 4 di square is equal to, so resistance force is sigma L into this area. This area is how? So if you see from this direction, so this area is given by this one. So this is resistance area, resisting area. Its area is calculated by using formula pi di into T. So if you simplify again, so here you will get sigma L is equal to Pi into di by 4T. So again Pi into di by 4T into eta c, eta suffix c. So eta suffix c means it is a circumferential joint efficiency. So if nothing is given, so you can take eta c is equal to 1. So this is the formula we are going to use to find the longitudinal stress induced in the thin cylinders. That means you can see longitudinal stress is pi into di by 4t, but tangential stress is pi into di by 2t. So here sigma t is 2 times the sigma L. Okay, so that sigma t is more than sigma L, means it is 2 times sigma t is 2 times the sigma L. Radial stress in the cylinder. So radial stress in the cylinder it is given. So radial stress at the inner point of the cylinder, radial stress is equal to whatever the internal pressure. Suppose internal pressure is Pi, then radial stress at inside point, inner surface will be equal to minus Pi. Equal to minus Pi, and at the outer surface radial stress is 0. At the outer surface radial stress is 0. At the inner surface radial stress is minus Pi. Minus sign indicates so pressure acts in this direction towards this surface, and resistance created by radial stress acts in the opposite direction. So that's why you can say radial stress is minus. So as the Pi is very less, sigma r is neglected in case of the thin cylinders. So in case of thin cylinders, so we are not going to consider the radial stress. Radial stress is neglected as the P is very small. Next is principal stress in thin cylinders. So principal stress means, so what are the stresses acts in the thin cylinders? Tangential stress, longitudinal stress and radial stress. So these three stresses are acts in the cylinder. So we take it as this is the maximum principal stress and this is minimum principal stress. Sigma 1, sigma 2 and sigma 3. If you return the sigma 1 is greater than, sigma 2 is greater than sigma L, sigma 3. Means sigma T is greater than sigma L is greater than sigma R. You can see this is formula which we already discussed, sigma T and sigma L. So here we are not going to neglect the sigma R. So that means sigma T here is greater than sigma L. So thickness is calculated using tangential stress. Means sigma T is always more than sigma L. For safety purpose, so we have to consider sigma T equation to find the thickness of the cylinder. So that's why thickness of the cylinder is given by T is equal to Pi into Di by 2 sigma T into eta L. Sigma T means what here? So that is tangential stress. So that should be equal to the allowable stress for the material which we are going to use to manufacture the cylinders. So next is stress in spherical vessels. So this is the spherical vessel. So it is again 50% is cut here to make the analysis. So again if you consider 50% of this 50% portion, so again force due to this pressure should be equal to the resistance offered by this stress. So here there is only tangential stress, there is no longitudinal stress. So here force due to pressure is given by Pi into projected area, means it is Pi into pi by 4 di square. Suppose if you project this area, so that will be circular one with inside diameter is di. So that's why projected area is pi by 4 into di. So that's why pi by 4 into di square is equal to resistance force. Resistance force is again if you project this, you can see this is the projected area of this. So its area is given by pi into di into t. That is resistance area is given by sigma into pi into di into t. Again if you simplify, so you will get the pi into di by 4t. Okay, so we are just introduced the eta c. Eta c means it is a joint efficiency. For spherical pressure vessel, sigma equal to sigma T is equal to sigma R. Here you can see spherical pressure vessel has twice the strength of cylindrical pressure vessel for given thickness. So here you can see maximum stress induced is given by Pi into Di by 4 times thickness. So that means stress for a given thickness, stress induced is less as compared to the cylindrical vessels. So that's why it is twice the strength of the cylindrical pressure vessels. So let us see one simple problem on cylinder. Storage capacity is 0.25 meter cube. Pi inside pressure 20 megapascal. Length of cylinder is equal to 2 times inside diameter. So it is made up of 28 material. Ultimate strength is 390 MPa. Factor of safety is 2.5. And we need to find the dimensions. So dimensions of the cylinder means what? Length, inside diameter and thickness. So these three parameters we have to find. So here you can say volume is given. Suppose if you want to find the first aim is whenever you want to find dimensions, so you have to first find the thickness. So if you see the thickness equation, what is the thickness equation of the cylinder is given by? So Pi into Di by 2 sigma T into eta L. So eta L is not given anything, so you just take it as a 1. Otherwise you just say it, neglect the eta L. So Pi is given, Di is not given, and sigma T means it is. So here you can say sigma T means allowable stress of the material. Allowable stress of the material is ultimate upon FOS. So sigma T is equal to ultimate means 390 by 2.5. It is 156. Means sigma T is 156. Pi is 20. Di we don't know. So how to find Di inside diameter? So volume is given. V equal to volume of the cylinder is given by pi by 4 into, it is storage capacity formula, pi by 4 into Di square into L. So it is equal to volume is 0.25 meter cube. So here one more condition is given, L equal to 2 Di. So you just simplify, you just substitute L is equal to 2 Di. So this equation becomes in terms of Di. So you just simplify that, you will get the value of Di. It is equal to 250 mm. Suppose if you substitute Di value is in mm, so you will get thickness is in mm. So substitute in this equation, always substitute pressure and stress in terms of the Newton per mm square, and Di is in mm, then you will get the thickness is in mm. So thickness is equal to 16 mm. Okay. So and length is equal to, already diameter we have calculated. So length is 2 times the Di, means diameter is 250, length will be equal to 500 mm. Means diameter is 250 mm. Inside diameter, next thickness is 16 mm, length is 500 mm. So these are the dimensions of the cylinder. Next, let us see one more problem. So it is combination of sphere and cylinder. This is the air receiver. Storage capacity is 0.25 meter cube. So this is the figure given. Complete storage capacity. It is up to here. It is a cylinder. Afterwards, it is a end is spherical shape. It is. Operating pressure 5 megapascal. Material is ultimate strength is 340 megapascal. Factor of safety 4. Neglect weld efficiency means eta L and eta C equal to 1. Dimensions of receiver. So dimensions of receiver means what we need to find? Its length and its diameter. This is length and its diameter, that is inside diameter, and its thickness. So those three parameters we need to find. First of all, its total storage capacity is 0.25 meter cube. That means how to find this formula? You can see here, from here to here it is cylinder, and from this point to this point it is 50 of sphere, and here also from here to here it is half sphere, means half sphere plus half sphere it will become full sphere. One sphere plus one cylinder. Total volume capacity is given by one cylinder plus this will become one sphere. That's why volume is given by pi by 4 into di square into L. So this is the volume of cylinder. Next, volume of the sphere is given by pi by 6 into di cube. And one more condition is given. L is equal to 2 into di. L is equal to 2 into di. So if you substitute this L as 2 di and volume is already given. So how much it is? Volume is 0.25. So if you substitute V is 0.25 meter cube and L equal to 2 di. So you will get the di value in meters. Suppose if you substitute value of V in meter, you will get value of di is in meter. It is 0.492 meter. That means it is 492 mm. So you can take it as a 500 mm. And if your diameter is 500 mm, length will be equal to 2 times diameter. So it is the 1000 mm. Again, thickness, we have to calculate the thickness. So here there are two sections. First is cylinder, next is sphere. So we have to calculate the thickness of cylinder and thickness of the sphere separately. So allowable stress for the material is 85. That is ultimate 340 by FOS is 4. 340 by 4 is, it is 85. Sigma T allowable stress is 85 Newton per mm square. For cylinder thickness we have to calculate by using the equation Pi into Di by 2T. So if you substitute sigma T value is 85. Pi is inside pressure is 5 megapascal. Di is 500 mm. So only unknown is T. You just find the value of T. So you will get the 15 mm. That means this thickness, cylinder thickness, its thickness is 15 mm. Next, spherical head. So for spherical head, this formula we have to use Pi into Di by 4 times thickness. So you will get thickness is 8 mm. Means, so thickness of the spherical head, this will be equal to 8 mm. Okay. So this is about the complete introduction to the cylinder, classification of cylinder, theory related to this thin cylinder, and problems on the thin cylinder and spherical vessels. Okay. So if you have any doubts regarding on this, so you can contact me. So thank you for watching this video. So in the next video I will cover the thick cylinder and problems related to the thick cylinder. So thank you all for watching this video. If you have any doubts, any queries, so if you're not understanding, so you can contact me. Thank you.